Hello everyone, welcome back. In this lecture, we're going to be discussing about CDC tool, Questa from Mentor Graphics. Questa 0in is industry standard sign-off clock domain crossing tool. A few years back, Mentor bought a company called 0in, which was the leader in clock domain crossing verification. We're going to be discussing the same tool and how you can set up the tool and verify CDC issues. A basic overview about the tool. All right. Questa CDC 0in tool. It works in 3 stages: static, dynamic, and metastability injection. So first, you would want to clear your CDC violations in a static mode. Good. After you are satisfied with the results, you have created necessary waivers, and there is no error or no CDC issues during the static analysis. Then you can move on to the dynamic analysis, where it's more extensive analysis in terms of the tool would write assertions to check the protocols wherever the clock crossings are happening. Okay, and then tool would try to simulate the circuit along with the assertions. Okay, the assertions are generated when you use the dynamic mode of the tool, and those assertions are needed to be compiled along with your regular test bench. You can use either Questa simulation environment, or you can use those assertions with the VCS or any other third-party simulator. Good. Then third step would be metastability injection. Once you are satisfied that you are okay with the dynamic simulation results, then you can further extend your simulation goal or your CDC verification goal as to have metastability injected in your design at certain time or at certain places or in certain modules, and it's an extension to the RTL simulation. Good. So it is very similar to the dynamic simulation, except that in metastability injection, the tool would try to inject the metastability in certain part of the design and then try to understand the behavior, okay, how it behaves in simulation. So what it means that you may capture a bunch of critical errors in that mode. Okay, most of the time, if we are satisfied with the static analysis, these all may be okay. Again, depending upon what kind of CDC strategy you have used. If, let's say, you are using closed loop CDC solutions, most likely these dynamic and metastability injection would be okay, where you are basically binding the clock domain crossings in a closed loop with a handshake protocol. But if there is an open loop solution where you just pass the signal from one clock domain to the another clock domain, and you just rely on that the signal is supposed to be high for certain clock duration, or excuse me, there is a certain pulse width, then it becomes important to at least check the dynamic check the CDC verification in the dynamic mode, or in other words, generate the assertions and simulate your design with those assertions. So you might be surprised that you catch protocol violation errors. Good. As I said, Static CDC checks for structural issues in your design, dynamic checks for data stability or protocol issues, and metastability injection checks for hardness of metastability. Good. For dynamic CDC checks, you need simulations, so it's tied with the RTL simulations. The good your RTL simulations are, the good your dynamic CDC results would be. Good. Metastability injection also needs RTL simulations. Good. Now, first step when you have the working RTL, this very first step for all Questa tools is very similar. You compile the Verilog or VHDL RTL code. How you can compile? It's simple, vlog and then your Verilog file. Second step, now it's the tool specific settings. Good. So in case of CDC, you define the CDC specific settings, what are the different preferences in a .do file. .do is another way Mentor uses .do. It's a tickle file. So if it's a simple tickle file, you can say do and tickle.do or something. In other words, these are tickle commands. And then step third is very simple. Then now you run the Questa CDC. Now initially you don't want to run in a GUI mode. It's a bit slower. If your design is very small, let's say very small block, you may not notice the speed difference. But if you are working, let's say multi-million design chip, and then my recommendation goes that you run the tool in the command mode. Okay. And command mode is simple. -c, if you use -c with qverify, it will run the tool in command mode. Step 4, after you run the tool is satisfied, tool compiles, it will give you the report. Okay, and you have to analyze different reports, design files, whether you have missed anything or not. So there are going to be a bunch of reports in the results or log directory generated. Okay, you can also see what different settings tool is taking, and if you have to adjust the clocks, resets, or constants, or constraints, or port constraints, or IO constraints, and whatnot, you can adjust those settings in your do file. Okay, and if you see there are violations, either you fix them, okay, and if you cannot fix, then it's a problem, right? Or if you see that, okay, my RTL is good, tool is reporting some garbage, okay, you can after analyzing, you can put waivers on those violations, but my recommendation goes that try to fix them, and you should not have a lot of waivers in your design. Maybe you forgot some signals to be constant, but let's say if it's a SoC with a multi-million design, you are integrating different IPs, it is sometimes difficult to get all the signals which are constants. In that case, you may want to use some waivers. And nevertheless, it is a very subjective question, okay, and it depends on the expertise of the designer or the CDC expert. But in principle, you should have less waivers and more constraints and settings for the tool. Okay. And if you are satisfied, you are good. If you are not satisfied and you want to have further debugging, you can invoke the GUI mode for the Questa CDC. Okay. How to invoke the GUI mode? Simply launch the qverify command. Qverify. Okay. All good. So 5 steps, or essentially these are basically more or less 3 steps I would call. Compile is by default for all Questa tools. Second step, you define all the tool settings, preferences, and remember this is not a one-time process. This is kind of a iterative process. You see the result, you're not happy, then you may want to chat with the designer, or you may want to update some settings for the tool. There are tons of different settings that the tool can run. These tools are based on formal. Okay, and the formal problems fall in the category of NP-hard problems, and internally these tools use Boolean satisfiability algorithms. Okay, so if you guys are familiar with computer science, there is a class of algorithm. um, they fall under the SAT, or satisfiability theorem. Okay, so these Boolean satisfiability problems are NP-hard problems. So there are approximate algorithms. So you can run the tool in different settings for the formal. Okay. So let's talk in detail how you can compile. You can compile Verilog or VHDL code via VCOM or Vlog. If you have VHDL, VCOM. If you have Verilog, Vlog. Okay. What it needs is design files and model sim init file or initialization file for the model sim, or the now it's the Questa toolset. Okay, and you need the work directory, and all the results will go of the compilation work directory. So remember, this vlog is sort of a think about a parser, checks syntax errors, other kind of basic checks. It's not a detailed check. So after the tool compiles and the design in the work directory, then the formal process starts, or the CDC tool compiles in its own database. It does a formal compilation. Okay, very simple. Vlog, you're on duty.v, vcom-f, duty.vhd. Very good. Second step, you can define the design settings tool preferences in a do file. So if I look my cdc.do file, okay, it will look like this. So I define the clocks in a separate clocks.do file, which I then call in a master cdc.do file. A simple sort of keyword to define clocks is netlist clock, and then clock period and whatnot. You can check this command on the tool documentation, or I may give another lecture on to detail how to define the different clocks. You can define the reset same way. What are the different resets in your design? Tool automatically can infer the clocks and resets. Okay, so if tool infers automatically clocks and reset, you have to review it, and then you have to say, okay, these are good to go. All right. And nevertheless, it is important to understand that you have all the clocks should be defined by the user with the proper clock period. Then the tool will give you the better results. Okay. Now, if you have constants in the design, let's say this signal is constant high or constant low, or other constants in the design, let's say higher port constant stays at logic 0 or 1 or whatnot. You define in a constants file. Preferences file, these are tool preferences, how the tool is supposed to handle FIFOs, for example, how the tool is supposed to handle the convergence, whether you are using convergence or not. Different tool preferences, there are 20 different tool preferences one can use with this tool. Okay, you can define all the preferences in a one preference file. Once you are satisfied, okay, I need these preferences, tool will run in that mode. Sometimes you don't want tool to spend too much time. Okay, so you can also put a effort low. okay, formal effort low. And if you want, okay, tool to do hard work, you can also set formal effort high, okay, but the runtime varies accordingly. If you have waivers, you can define waivers in a separate waiver file, okay. For the preferences, CDC preference is the keyword or the tool command. Same way, waivers, CDC report item. These are keywords. Further description on the full command is needed in this file, but this is just to give an idea or an overview how you can handle big designs. Okay, then you can run the tool CDC run -d design top. Good. CDC run, if you are running, if you are in a dynamic simulation mode with the -, protocol, it will generate the assertions. Those assertions then you can compile and run the RTL simulation. Okay, and then so CDC is here is pretty much you are done. A further check would be good to know the resets, if there are reset domain crossings. Okay, so I have discussed reset domain crossings, different clock domain crossings in previous lectures. If you have not watched those lectures, my recommendation would be to watch all clock domain crossing lectures at my LEPROF channel. Okay, that will give you a better idea before going further in detail. Okay, and then simply final step would be to run the Questa tool. Okay, qverify is the command. Very good. What it needs: your work directory, which you have design information after vlog compilation, and then your preferences file, cdc.do file will go with the qverify, and then it will generate the cdc.db database. Remember that you can always change the names and whatnot. Very simple. qverify -od says output directory. Log is default. I would say put it in the results directory. -c says the command mode. -do is the preferences file or the do file, which has the preferences for the tool and other constraints and settings for the tool. Good, very simple. And then if you are not, and then you can check the results in the GUI mode and debug it. GUI is basically helping you to debug, but if you are an expert, you don't need to launch the GUI. You can work with the log files and report files and fix the issues accordingly. Okay, very simple how to launch the GUI, qverify, and then the your database, wherever the database you have stored. In my case, I stored in the results directory. So very simple here: qverify results cdc.db. Good. Now, common kind of violations you may see when you run the zero in CDC tool. No sync. Okay, there is no synchronizer. Combo logic before sync. This is another common kind of violation where the designers are not not very careful, that they put some kind of AND logic, NAND logic, or some combinatorial logic before the synchronizer. Okay. Then multibits are crossing across the clock domains, fan-in and different clocks, reconvergence of the bus or single bit, reset domain crossings. Okay, no sync is very important. Combo logic before synchronizer is also very important, and same way the other settings. So once you you fix the no sync, combo logic before sync, most of other violation may go away, or if it is still remaining, you may have to deal with them. Multibits across domains are a bit trickier. you just don't simply want to pass multibits. We have discussed this case in previous lectures, where I discussed the CDC, how to cross multiple bits across clock domain crossing. So you may need some kind of extra logic or state machine in sending clock domain, also receiving clock domain. You may want to use the handshake protocol in those scenarios, or convert the parallel bits in terms of gray code, and then send the signal across the clock domain, so that only one bit is toggling. All right. Reconvergence is another issue where you would want to be very careful. Okay. Reset domain crossings, same way. Good. So let's talk about the no synchronizer quickly. However, I have discussed most of these scenarios in previous clock domain crossing lectures. If you have not watched those lectures, please do watch. You will get a better idea. I'm gonna be quickly skimming through these issues in this lecture. Okay, no sync, where you are sending your TX signal, or your TX clock domain signal is going to second clock domain, receiving clock domain signal, and ideally you should have a synchronizer here, but there is no synchronizer. Okay, there is a missing synchronizer. Good. Combo logic is another common kind of violation, where your TX clock domain signal, okay, is going to RX clock domain, and you have synchronizer in place. However, just before the synchronizer, you have some kind of a multiplexer. Okay, and these multiplexers may come in form of, let's say you do the DFT insertion after the clock domain crossing check, okay, or after you have modified the design according to the CDC. Then you may encounter this mux. Most of the time, one signal, okay, these two signals are constant. The select signal is constant, and the other signal is constant if it is a test mux or a DFT related mux or DFT mux. But if it is not, then you got to be very, very careful that this signal should not be switching, other signal should not be switching. If both two signals switches at the same time, we are kind of toggling this signal too much, okay, because we don't know at what time this signal will toggle. Means that the synchronizer will go very frequently in metastable state, which is not good for overall chip. Okay, so that increases the probability of failure. Okay, or MTBF number gets increased exponentially. Okay, means that your chip is, or your synchronizer flop is getting into metastable state very often, not very good. I have discussed this issue of the MTBF, how the MTBF calculation works, in another lecture called metastability. You may want to watch that lecture, very helpful. Good. Okay, so as we said, combinator logic before synchronizer, multibits. Okay. So let's say if you have a bus which is crossing across the clock domain, this is not good, this is not good, you have to deal with it. So you cannot just simply put, let's say if it is 10-bit wide bus, you just cannot simply put 10 synchronizers. It's very, very bad. Okay, so there are different strategies for multibits. I have covered the strategies for multibit in other CDC lectures. You may want to watch them. Okay, please watch CDC multibit synchronization techniques if you are dealing with this issue. And in real chip, all those issues are there. All those techniques you may want to use, or all those techniques need to be there, depending upon whether you use open loop, closed loop, or whatnot. But the CDC issues must have to be fixed before you tape out. All right. Fan in different clocks is another kind of violation, where you are feeding fanning in to the RX clock domain, and the signal is combined via a combinatorial logic, and this signal which is coming to your RX clock, okay, this is a result of mating of these two signals. Let me put it mating. However, you are combining these two signals, TX signal 1, TX signal 2, coming from two clock domains, okay, via multiplexer and going to RX clock domain. So this is a fan in different clocks. You have to deal with this situation. Okay, so this is another kind of violation. I have discussed this scenario in past, how to deal with it. Okay, but in general, if this situation comes, you may want to shift this whole mating logic to the RX clock domain and properly synchronize the this signal before using in the RX clock domain. Okay, this is bad. Good. Now reconvergence is another issue where you got to be very careful. I have discussed this reconvergence, how to deal with it, what is the implications of reconvergence in one of the CDC lectures. Please watch that. But in general, what happens that your TX signal, okay, you are sending two TX signals, okay, coming from the same clock domain and going to the receiving clock domain. However, these two signals, okay, are separately synchronized. You see, separately synchronized and then combined together via this AND logic. And this is bad. This is very bad, because you don't know what time this TX signal will reach to this AND gate, and you don't know what time this TX RX or the TX signal 2 converts to RX signal 2 will reach to this AND gate, and the resultant would be this toggling thing here. And there will be you would want to avoid all sorts of all sorts of I'm trying to put it in good words, all sorts of logic which toggles the input signal of the D flip-flop too much. Too much means that otherwise it becomes another clock. Okay, so clock toggles, right? And at each edge you are sampling the signals. So think about if the RX clock and this signal is toggling too much, it's a dangerous thing here, okay, because this flip-flop may go into metastable state sooner or later. Okay, so you may have to put here one more synchronizer in order to properly use this signal. So one more synchronizer after the AND gate, or do something else. Okay, so this is a reconvergence issue here. It is reconverging at this AND gate. This signal is not stable. This is very dangerous here. The output of this AND gate going to D flip-flop. It will make this D flip-flop getting into the metastable state. Not very good. So they have to deal with it. Good. Okay. So here at this point, the signals are diverging. Okay. This is the output of one AND gate diverging to two clock domain crossing signals, okay, going to receiving clock domain and getting combined again or converging again. Very bad design practice, very bad. Okay, so this is what is reconvergence and divergence means. So signals are diverging and getting converging. We need to deal with this. It's not very good in this fashion. Okay, so there are different techniques one can use, either to move this signal, both of these signals into first clock domain, and just only pass one signal to the second clock domain. So always remember, one signal or less signals passing to the other clock domains are good. If they are converging somewhere, we need to be very careful. Okay, in some cases it might be okay if you say that, okay, my design is not in my design I have some kind of a reset state or some kind of a thing, But again, it's very hard to justify, so have to deal with this. Need to be very, very careful in reviewing the design if these issues are present. Okay. All right. So TD1, as I said earlier, is the time, TD2 is the second time, you don't know, and this is bad, very, very bad. A few notes about the CDC. Always double check your tool settings, your different clocks, your black boxes, your constants, ports, resets. Always double check the tool settings. You may have to run the tool iteratively multiple times, okay, before you are done with the CDC verification. Check the clock tree, reset tree, if there are inferred clocks, and reset. Okay, there are inferred clocks, make sure that you have proper clock definitions in your clock file and all the clocks are properly captured. Very important. Run the tool with and without enabling the formal engine. Okay. Run the tool with and without the reconvergence enable settings. Review preferences and waivers applied. Plan for the gate level CDC verification after logic synthesis. Because what may happen, the logic synthesis tool may put certain logic which may violate the CDC. Okay. So plan in advance for the CDC when you are working on a full chip. A lot of problems, a lot of chip ICs are screwed up because of the clock domain crossing issues are not being taken seriously by the designers or by the design primes or by the design leads. Plan in advance. It's very important that the CDC issues must have to be cleared before tape out of the chip. All right. If you have CDC issues and if you are looking for training, workshop, you may contact us. We would be happy to help you for your design related to the CDC. All right. Thank you very much, guys, for listening. Please do subscribe, comment, and these days YouTube has YouTube always keep updating settings things. So they have some kind of a bell icon. So you may click on that bell icon as well. That enables to receive notification of my new lectures as soon as I post them. So thank you once again, and if you are looking for any help related to your CDC issues in your design, we would be happy to help you. Please contact us. Thank you very much. Bye for now.